Okay, so today I want to go over something called colligative properties. And before I go over this, I just want to go over some applications of this in nature. So when you think about like when it gets really cold outside, we see that some animals are able to survive during the long winter. Um, and also we think about trees. Trees are also able to survive very cold temperatures. So one reason behind this is that some animals actually have like a natural antifreeze in their bodies. So this happens with some types of turtles as well as snakes, and some of our trees also have it like a natural antifreeze. So just to give you an example, we think about the sugar maple. It actually has, if you know, like you can tap sugar maple trees and get maple syrup. The reason why is that their sap actually has a sugary substance in it. And when we tap the maple tree and then boil that down, we can get maple syrup. So maple syrup actually boils at a much higher temperature than pure water, and also will freeze at a lower temperature than pure water. And that's because of the sugars that are present. So we're going to go over different types of colligative properties. So colligative properties depend on the number of solute particles present in solution. It does not really depend on what the solute particle is. It doesn't depend on the identity, just the number. So some examples of colligative properties we're going to be going over are vapor pressure lowering, and we'll go over why that happens. Boiling point elevation, we'll also go over why that happens. And then finally, melting point or freezing point depression. So when you have a substance in solution, a non-volatile substance, so this, what happens is if you look at like your pure solvent here, it's very relatively easy for the solvent particles to escape from the surface of the liquid and turn into a vapor. And thus you have a certain vapor pressure on over your solution. If you have a non-volatile solute present, what that means is that the solute, and that's the yellow particles here, kind of get in the way of the solvent, and that's the green particles here, get in the way of their ability to escape from the surface of the solution. As a result, fewer of the solvent, and those are the green particles are actually able to escape and turn into a vapor. So that way, the vapor pressure is lower, the pressure of that vapor is lower, and it's more difficult for the solvent to evaporate when you have a solution. So whenever we have a solution, the vapor pressure of the solution will be lower than that of the pure solvent as a result. With freezing point depression, what happens is that the presence of the solute, and that's in this right-hand picture here, those are the green particles there, makes it more difficult for the solvent, in this case water, particles to freeze. So you think about here we have the solute, and that gets in the way of the water molecules being able to hydrogen bond with each other and then form nice water crystals. So you actually have to get to lower temperatures for the water molecules to be able to line up and form crystals and thus to freeze. So that's why the freezing point of the solution will be lower than that of the pure solvent. So on the bottom of your solubility curve, you actually should notice that there's a table with the boiling points of different solvents. These are different solvents. We have water, benzene, ethanol, carbon tetrachloride, and chloroform in this table here. And then we have what's called the boiling point constant, and then the freezing point and the freezing point constant. So the change in the freezing point, which we'll go over first, is found by this equation, delta TF is equal to I, and we'll go over what I is and how to calculate it, Kf is the freezing point depression constant, and then M is molality. So make sure you write that equation down into your notes. So when once we find our change in freezing point, what we then do is we subtract that value that we calculate from the freezing point of our solvents. So in the case of water, Kf is 1.86 degrees C, and that's over molality. That's not meters. So over molality. So we use that for water. And then once we find our delta TF, we subtract the value we calculate here from 0. So whenever we have a solution, water will have a negative freezing point. Okay, so one thing that's important to realize is we're talking about non-volatile solutes and something that would actually go into solution. So we think about sand. We know from any of you who've gone to the beach, the sand definitely does not dissolve in water. So if you've ever gotten a bucket of ocean water at the beach, you will notice that sand will kind of drift to the bottom of that bucket because it's not soluble. So your solute has to actually be in solution. So sand won't ever go in solution. So that's not going to make a difference in our freezing point. Rock salt, sodium chloride, we know goes into solution. And then calcium chloride also goes into solution. So these two would be good to lower the freezing point of your water. And then they would be good to actually keep the water from freezing on the roads in the wintertime. It would make a difference with the roads not icing up as quickly. All that sand would do it would increase traction on the road. It make the roads less slippery as a result, but the ice would still form on the roads just as readily. Okay, the second type of colligative property we're going to go over is boiling point elevation. So if you have a solute, that actually is going to raise the boiling point of your solution. So what happens here is our pure solvent. We have a lot of particles that are escaping into the vapor. If we have a solute present, what happens is these solute particles kind of get in the way of the solvent being able to escape into the vapor, and thus you have to increase the temperature even more to get this to boil. Okay, applications of boiling point elevation are things like your antifreeze in your car. So your antifreeze in your car actually does two different things. In the summertime, it keeps the water in your radiator from boiling because it takes a higher temperature for that water to boil with the antifreeze present. And then in the wintertime, that same antifreeze in your car keeps the water in your radiator from freezing because you actually have to go to lower temperature for the water to freeze, so then your engine doesn't freeze up. So in the summertime keeps the engine from overheating, and the wintertime keeps things from freezing up. Okay, so the equation for the boiling point elevation is very similar to that for the freezing point depression. So here we have a change in temperature for the boiling point is equal to I, and again, we'll go over what I is. Kb is the molar boiling point elevation constant, which is again on your in the table on your solubility curve at the bottom of that sheet. And then M is the molality. So once we calculate delta T sub B, we add that change in temperature to the normal boiling point of our solvent. So for water, we would calculate delta TB, and then since water normally boils at 100 degrees Celsius, if it's pure, we would add that delta TB to 100 degrees Celsius to determine the boiling point of our solution. Okay, so one way to remember that boiling point is elevated and freezing point is depressed is that if you think about, here's an alligator, the boiling point is obviously higher than the freezing point, so boiling point would be the top jaw, freezing point would be the lower jaw. And then when you force a solute into alligator's mouth, the mouth opens even wider, resulting in the boiling point the top jaw going up, the freezing point of the lower jaw going down. Okay, so if you look at both equations, in both equations, delta T does not depend on what the solute is, but on how many particles are dissolved, and we'll go over why that's the case. So this I, the reason why that's the case is this I is actually called a Van 't Hoff factor, and it's the number of particles produced per molecule or per formula unit. For covalent compounds, since they don't break up when you put them into water or into solution, I is equal to 1. Ionic compounds actually dissociate when you put them into solutions, so I will depend on the number of ions present in both positive and negative ions. And remember, M is a molality, so all this depends on is the molality times the number of particles that you have in solution. So if you think about something like glycol is actually a covalent compound, and for that one, I would equal to 1. But if we have something like sodium chloride, let me just go over this real quick. Sodium chloride actually breaks up when it's dissolved in water. So if you think about sodium chloride, it's composed of a sodium ion. It's composed of a sodium ion, and this would be in water, that would be aqueous. And then chlorine ion, and when it's dissolved in water, that's also aqueous. So I, in this case, would equal to 2. If we look at calcium chloride, this is actually composed of a calcium ion. So in water, you would have calcium ions present when it's dissolved, and 2 chlorine ions. So this 2 becomes a coefficient. So here, I is equal to 3. And finally, if you look at calcium phosphate, the polyatomics do not break apart in solution, but what happens is when this dissolves in water, you get 3 calcium ions in solution, and you get 2 phosphate ions in solution. So here, I is equal to 5. So the I for covalent compounds, and sometimes covalent compounds are referred to as non-electrolytes. And that's because they don't conduct electricity, and so an electric current will not flow through a solution of covalent compounds because there's no charges to carry that current. So covalent compounds are often referred to as non-electrolytes. And they will have I is equal to 1 because they do not break up in solution. And ionic compounds, you have to look at the formula, determine how many ions, cations, and anions you have. You have to use the subscripts to figure that out. And then you can calculate the I. Okay, so I want to go over a few different problems to show you guys the problem-solving process. So I'm going to do one on this slide here. Okay, so we have 5 moles of ethylene glycol dissolved in 5.0 kilograms of water. So what is the boiling point of our solution? So when you're doing problems like this, water is normally going to be your solvent, but it may not necessarily be your solvent. So always pay close attention to the wording of the problem. So typically when you see OH, unless you see it with a metal like sodium, this is going to be just a hydroxy group like we would have like on alcohols. And this is actually a covalent compound. If you notice here, it's paired up with carbon and hydrogen. So that's telling you it's more like an alcohol group. So this is covalent. So in this case, I is equal to 1. So always be careful if you see a hydroxy group. Only assume it's ionic if you see it paired up with a metal. If you see it paired up with carbon and hydrogen, then you have an alcohol, which will have an I is equal to 1. So here we're asked about the boiling point. So we have delta TB is equal to I times M, which is our molality, times K sub B. So I want to go to your solubility curve and just show you this. But if you look at it here, we have water, and you notice here there's K sub B and there's K sub F. Always make sure you're using the correct one depending on the problem. Since we're talking about boiling, we're going to be using K sub B, which is 0.51. And you notice here the units are slightly different than I showed you on the slide. So remember, kilograms per mole is actually molality. So this is actually delta C divided by molality, lowercase m. So you could also write it out like this, which is really helpful if you're having to make sure units are canceling out. You may want to use kilograms per mole instead. So let's go back. So we have I is equal to 1 in this problem. And we have to calculate the molality. So molality, they've done a lot of the work for us. So we have 48 moles over 5 kilograms. So let's divide that. So 48 divided by 5 gives us 9.6 moles per kilogram. So that would be 9.6 M. So here, I'm going to plug that in times 9.6 moles kilograms, or I could have put 9.6 M, and then I'm going to use 0.51 degrees C kilogram over mole. And you notice here, kilograms cancel out, moles cancel out. If I'd used degrees C over M, I would have also wanted to use 9.6 M to make sure things are canceling out. So I get here 9.6 times 0.51 gives me, and this would be 4.896 degrees C. And I'm not going to worry about sig figs until the end. So again, let's look at the sheet, and we see that the boiling point of water is 100 degrees Celsius. So I'm going to do the boiling point, the solution is TB is equal to 100. Remember, it's boiling point elevation plus 4.896. And remember, this should be actually 2 sig figs. And you can assume in this case that 100 is like 2 places past the decimal. So, because sometimes you'll lose a lot of information if you round to only like the 100th place, because then it would appear that hadn't changed. But 100 plus 4.986 is 104. 104 point, and this would be 9 degrees Celsius. Because this, remember, is 2 sig figs, and we're assuming that 100 has the same places after the decimal. So that is our boiling point. So it is elevated. So always remember that you're adding that. Okay, so let's do another one. Here we have calcium chloride. So here we have to actually calculate the molality, and we also have to calculate the I, because calcium chloride is ionic. So whenever you have something that's ionic, you're going to have to calculate the I. So remember, with calcium chloride, in solution, this will form a calcium ion plus 2 chlorine ions. So we know that I is equal to 3. Okay, so we also have to figure out our molality. So we have 55.5 grams CaCl2. And then we're going to calculate the molar mass of calcium chloride. So let me get my periodic table out, and let's figure that out. So we have 40.078 plus 2 times 35.453 gives us 110.984 grams in 1 mole. So if we do that, we get 0.500 moles. And then the molality is equal to 0.500 moles divided by 2.0 kilograms. And this is kilograms. That's good. If it weren't, we would have to convert that. And then we divide that by 2. And we get 0.250 moles per kilogram. Okay, so this one's asking for the freezing point. So we're going to be using delta T. F is equal to I, which is 3, times our molality, which is 0.250 moles over kilograms. And then again, we have to look at our sheet, and we see that the KF for water, so now we're looking at KF, is 1.86. So always be very careful if you're doing freezing or boiling. Times 1.86 degrees C kilogram over mole. And then we're going to get for this times 3 times 1.86. We're going to get 1.395. And I'm keeping a lot of sig figs, but here I can see the minimum I have is 2. So when I take 0 minus this, I'm going to get negative 1.4 degrees Celsius. So you can assume here this should have 2 sig figs, and you can assume that 0 degrees Celsius has one place past the decimal, so you don't lose too much information. So that is the freezing point of the solution, is 1.4. It's not positive 1.4, it's negative 1.4 since we subtract our delta T. Okay, so those are typical problems when you have to calculate either your freezing point or your boiling point. Now I want to do a problem where you have to kind of work backwards. So let's look at your sheet that you have for homework. Okay, so let's go down and let's see. This one's asking for you to work backwards. It's saying, what is the molecular mass of a non-electrolyte if 22.4 grams of the compound dissolved in 250 grams of water gives a freezing point of negative 0.93 degrees Celsius? So in a situation like this, let's do this one together. You're going to have to work backwards, and this information here is going to allow you to calculate the delta T. So you have to remember, water has a freezing point of 0. So to have a freezing point of negative 0.93, we know that delta TF is equal to 0.93 degrees Celsius. So we have this information. We also know it's a non-electrolyte, so that means that I is equal to 1. And we know that we have water, so we have a KF. So we have on the sheet, the KF is 1.86. So KF is equal to 1.86 degrees C kilograms over mole. Okay, so let's plug this in. So we have 0.93 degrees C is equal to 1 times 1.86 degrees C kilograms over mole, and then times our molality. So now we're going to solve for our molality. So 0.93 divided by 1.86, and that gives us a molality is equal to 0.5, and I'm going to have 2 sig figs because of this. Actually, because of this, 0.50 moles over kilograms. Okay, so now we're going to have to solve for moles. We're going backwards. So now we have the molality, remember, is equal to mole over kilograms. So now we're going to plug that in. So we have 0.5 mole over kilograms is equal to X. That's our number of moles. And then we have to convert this into kilograms. So this will be 2.25 kilograms. So we have that. So if we do that, 0.5 times 0.25, we get X. Our moles is equal to 0.125 moles. And now we're going to find our molar mass. So we have our grams. So now we could do 22.6 grams over 0.125 moles. And we get our molar mass is 180 for sig figs grams per mole. So that is our molar mass. So that's a situation we need to work backwards. Okay, so I want you guys to try the problems on this sheet, see if you have any questions, and just let me know if you need help.